Welcome, ladies and gentlemen. May I have your attention, please? Thanks. So when we go to evaluate an expression, middle school style, it's as easy as plugging in my variable values everywhere I see that particular variable, following the order of operations, working it out, and getting another value. So let's go ahead and rewrite my expression, except everywhere I see a B, I'm not going to put B, right? What am I going to put? Luke? Good, thank you. And everywhere I see an A, I'm not going to put an A. What am I going to put? Tyler? Good, thank you. And so we'll go ahead and plug in those values. Everywhere I see my B, everywhere I see my A, we'll go ahead and plug in those values, and then we'll follow our order of operations and evaluate. Make sure you're being careful with your order of operations. I put a parentheses, right, everywhere I do a substitution, because it'll remind me I'm not going to take -2 times -1 and get 2 and then square it and get 4. Instead, I'm going to square my -1, then I'm going to multiply by the -2 out front. And so I want to make sure we're being careful with our order of operations, we're being precise, and we're following our PEMDAS. So here we go. 5 times 2, 10. Minus a -1 is the same as plus a +1. Remember, subtraction is just adding the opposite. Logan?
It's +2 on the last one.
For the... Oh, right here. Thank you very much. That was my mistake. I appreciate that. Thank you, Logan and company. So here we've got, this is not 2 times -1 is -2 squared is 4. It's the -1 squared and then times the +2. So did I fix that now? Excellent. Thank you for your help. I appreciate it, guys. So here we are. We're going to do +2 times, and -1 squared is -1 times -1. That is a +1. And so this is just +2 times 1. Now we can go ahead and finish it out. It looks like 10 plus 1 plus 2, put it all together, and we have 13. At this time, I'd ask that you raise your hand if you've already had 13. So, well, it's already had 13. Woohoo! If you didn't, let's go ahead and fix it. That's okay. Order of operations, we want to make sure we're ready to go. We need our order of operations not just to evaluate expressions, but also to reverse and undo to get our solving steps, right? Our recipe for success when we're solving equations. Let's go ahead and take a look at the second one. Speaking of order of operations, goodness, we want to scan the problem and find, right, any parentheses, because PEMDAS, please excuse my dear Aunt Sally, comes first. No parentheses, so we'll move down to E, exponents. Are there any exponents I need to evaluate? No, and so we're all the way down to M and D, PEMDAS, multiplication and division. If there's both multiplication and division, we go ahead and perform those operations in order from left to right. And so here we're going to go ahead and do the 16 divided by 2 before we do the 2 times 4, right? We wouldn't do the 2 times 4, we do 16 divided by 2 first, because it's furthest to the left like we read a sentence. So here we go, 16 divided by 2 is 8, still have the times 4, minus 10 plus 5, still have multiplication and division. Now we'll go ahead and do the 8 times 4 is 32. Still have the minus 10, still have the plus 5. Done with multiplication and division, now we're all the way to addition and subtraction. So now I can perform them in order from left to right. So I'll do the 32 minus 10 is 22. 32 minus 10 is 22. Still have the plus 5 chilling. And finally, we can get to the 27. Raise your hand if you also got 27. Anybody follow it all the way to the end with the, oh, hey, that's great news, ladies and gentlemen. Nice job. If you didn't, that's okay. Fix it. That's why we take this time at the beginning of class to take care of our bell work together. Awesome. What kinds of questions do you guys have on our bell work today? Okay, so we've got a great big day in store for us. First, we're going to go ahead and take care of our mega assignment number 2 check. So at this time, if you go ahead and take out your assignment number 2. You've already shown me your reading questions, 1, 2, and 1, 3. If you're eligible for them, you know who you are. If you didn't complete them, then your maximum score for Infinite Canvas will be at 4. Recall, this is how we grade homework in this class. Everybody, we need our pencil for our completion grade, right? Our pencil is what we use to get our completion grade. What we're going to do is count up those number of problems that you completed. Out of our book problems, I think there was 21. I think there were 11 from our rewriting formulas worksheet. 21 plus 11 is 32 total problems. This includes your book sections and your worksheet. Give yourself credit for those you completed out of your book work and your worksheet, the two-sided worksheet. If you did all of them, then you get a 32. If you did your book work, we didn't do that separate worksheet, then you get a 21 out of 32. If you did the worksheet, but you didn't do any of the book, then you get 11 out of 32. So count up the number that you completed. If you did it all, you're 32 out of 32. Divide, enter, multiply by 4. This is your completion from problems. If you did the additional reading questions 1, 2, and 1, 3, you can add 1 to your score. Round to the nearest half point last. And your only choices are whole numbers or 0.5s. And so you're going to go ahead and round your final infinite canvas score to the nearest half point, and then box that nice and big on top of paper and pencil. Now we're going to go ahead and switch over. We're going to switch over to our grading pins. Our grading pins, we go ahead and keep track and get an idea of about how well we're doing. We write an accuracy fraction at the end. Out of how many we did, we're going to make an accuracy fraction. If you did all 32, my accuracy fraction will be out of 32. If you only did the worksheet, your accuracy fraction will be out of 11. Your accuracy fraction is always out of the number you did. And now we're going to keep track and get about. Don't get caught up on if there's multiple letters. If there's 4 letters, you can just take off a quarter point for each letter wrong. If there's 3 letters, you can take off a third of a point, 0.3333 for each one you're wrong, and it's about. This does not affect your grade in Infinite Campus. That's why it's okay if you do a little bit of rounding here. I want to see about how well you're doing. You need to see about how well you're doing, and you want to see that immediately. And so we do this each day in class so you get that immediate feedback to see how you're doing practicing with the material. What questions do you guys have on your Infinite Campus box score? Everybody put a box on it. Some people didn't put a box on it. Last time, everybody good box your Infinite Campus score and pencil. Now we're going to go ahead and go with pen. And again, some of these are make your own answer. Answers vary. We'll go a little bit quicker because I want to make sure we get time for our practice quiz at the end too. It looks like number 1 is about 45,600 cubic inches. Number 2, T is about 75 seconds. Number 3, if she has 122 nickels, her collection is worth $13.90. So we did an evaluation there. Number 4, negative 85 equals negative 5n, so n is 17. If her collection is worth $19.15, she has 17 nickels. Number 5, y is 8. Number 6, z is 0. 7, x is 1.5. 8, h is 15/4. 9, x is 120 19ths. You could change that to a decimal. All right, that would be a little bit over 6. And then 10, negative 3 plus 9y. Number 12, n is 9/5. B checks out, 17. T is 72/5. 18, P is 21/2. 19, Z is 10. 20, N is 1200. 21, N is 47. And we're moving and shaking because we want to make sure we have time for our practice quiz. Remember, your accuracy fraction is about how well you're doing. Second section. Yeah. 20 N was about 1200. So we can clear the fractions.
No, not 20. I was looking at 19.
Oh, I'm sorry. In 19. So my evaluation there looks like I distribute through the parentheses. Don't forget the negative. So I plugged in 2z. Distribute through the parentheses, combine like terms, same side, same operation. Then opposite side, opposite operation. And I'd be happy to take a look with you, Margot, during the practice quiz. We have some time at the end if you want to look at it individually. Make sure that you're good to go. So Z was 10 at the end of the day, and you'll get this back. Second section, 1-7. B is about 1,963.5 cubic centimeters. 2H, 4A, and then S respectively. 5V, B and H. 17, A, X is 16. B, X is negative 32. Letter C, X is negative 487. Woo. Bookwork. Bookwork. Okay, let's switch over then to our worksheet. 1 page, 2-sided. 1 page, 2-sided. We showed our forward steps there, and we went to a kind of our accepted abbreviations. For multiply by 3, we'll just say times 3. For take the square root, we'll just put a little square root, and so on and so forth. Then we reverse and undo to get our solving steps. Applying those solving steps in order to both sides of my equation will produce our solutions, and so here we go. Solving equations, rewriting formulas, worksheet letter A, x is 300. B, x is 8. C, x is 104 thirds, and you could certainly change that to a decimal, right, if you wanted to. For now, we're concerned with our order of operations. D, x is 60. E, x is negative 10/9. F, x is negative 13 thirds or 1. That was an example where we had to split up the absolute value bars. We went ahead and made another example of that so that in class today we'll be able to practice with the absolute value bars, because that's a place that can be tricky. We've got multiple solutions when we're solving absolute value, and so we'll go ahead and see how it is that we can solve absolute value equations, and we'll do that again in class today. Actually, we'll write down the absolute value one. In the meantime, we'll continue on with our formulas. G, R is given by the positive and negative square root of A over pi h. Recall, we need to consider both the positive and negative square root anytime we undo squaring. In our activity, when we took the square root of 25, our path broke apart because there's two numbers such that when squared equal 25. One of them is 5, one of them is negative 5. And so when we take a square root to undo squaring, we have to include both the positive square root and the negative square root. Two different solutions, and that's why there's a plus and minus right there. H, A is given by md squared minus c all over b. And I, c is given by md squared minus ab. Almost there. J and K. So J, two solutions. Again, a positive and negative square root of quantity AB plus C all over M inside the radical. K, it looks like B sub 1 equals 2A over H minus B sub 2. Recall that dividing by 1/2 is the same as multiplying by 2. And so if you have a 1/2 on the bottom of a fraction, that's the same as a 2 on top of the fraction. This is the preferred form because it does not contain a complex fraction. That is, no fraction within a fraction. That's kind of bad math manners to leave a fraction within a fraction. So anytime you have that 1/2 on bottom, that's the same as a 2 on top. Okay, as you're finishing up, please give yourself an accuracy fraction about how well you did. We'll go ahead and, oh gosh, we're going to have separate things. So bookwork on top, worksheet on bottom. You guys would start to tape on this side. Rick and Olivia, if you guys start the staple on this side, we're going to go do bookwork on top. Worksheet on bottom, staple it together, make sure you're in the Canvas Scores box, make sure that your accuracy fraction and pen is circled at the top. Thank you guys for passing the staple on, I appreciate that. Be ready when you receive it. Bookwork on top. Are you guys still waiting for the stapler? Okay. Good. Awesome. Awesome. Keep it going. All right. After your entire row has gotten a stapler, let's go ahead and pass straight forward. Straight forward, no left, right passing. If you need an assist, that's fine. And then forward, make sure they're facing the same direction. I appreciate your help. Did we get a stapler? Very good with assignment number 2. Very good. Awesome. Thank you for your help with that. I appreciate that, ladies and gentlemen. Okay. So what we want to do is make sure that you're comfortable handling solving equations that have the potential for multiple solutions. So what I want you to do is think about in our notes and our activity from day 2, there are 2 different situations where we could have multiple solutions. Go ahead and tell your partner which 2 kinds of equations could have more than one solution up to this point. So quietly tell your partner which 2 kinds could have more than one solution. Okay, so where can we have more than one solution? Marina and Heather? Yep, so we had squared equations. We could get 2 solutions if we solve the squared equation by taking square roots, because we have to consider, right, both the positive and the negative square root. We'll count that as one kind. So we've got squared equations could have multiple solutions. What other type of equation could have multiple solutions? What other type? Taylor and Mark? Absolute value equations could have multiple solutions. So we're going to take a look at those in a little bit more detail today to make sure you can handle those. All right. So everybody, if you could direct your attention to your day 3 handout now, the stapled packet, hole punch. Everybody find k squared minus 8 equals 28. Again, we can apply our process of reasoning, right? Our process of reasoning, reversing and undoing our forward steps to get our recipe for solving steps, right? So work with any equation so long as the variable appears once on one side of the equal sign, and here it does. So if I were to cover up this equation and pretend it were an expression that I'm plugging in a variable value k for working out, the first thing I would do in my Bell evaluate, number 1 would be square it. So I go ahead and have square it as my first forward step, and then subtract 8. So to get my solving steps, we'll simply reverse and undo. So if the last thing I did in my evaluation was subtract 8, I'll go ahead and reverse and undo that to get my first solving step would be add 8. And then here, right, is where Marina and Heather are talking about. When I undo the squaring, I have to consider 2 solutions, both the positive and negative square root, and I'll write that as my inverse operation. So I'll take the positive and negative square root. Let's go ahead and apply those solving steps in order now. First step was add 8 to both sides, just like you're used to for middle school. After adding 8 to both sides, I get k squared equals 36. And now we'll go ahead and take the positive and negative square root. That is to say, if k squared equals blah, then k is given by the positive and negative square root of blah. In this case, blah was 36. Sometimes this will reduce, sometimes it won't reduce. But either way, we'll be able to break it up into my 2 separate paths, like you did in the activity. Right? In one case, k is given by the positive square root of 36. In the other case, k is given by the negative square root of 36. So what's the positive square root of 36? That works out nicely, doesn't it? And in the other case, k equals the negative square root of 36. That's negative 36. quick check at my original. I'll grab onto the negative one, right? Our negatives, pesky little buggers, will go -6. Quantity squared is positive 36. Minus 8 does equal 28, so it checks out. What questions do you have about our multiple solutions from squaring equations? Let's take a look at our absolute value. So for absolute value, right, absolute value, we've also got a potential for multiple solutions. We saw before that deals with a distance number. There's two numbers that are a given distance away from 0 on the number line, and you remember that from middle school is your definition of absolute value. If I ask you what two numbers are 7 units away from 0, you tell me 7 is 7 steps away from 0 on the number line, but so is -7. Both of those are 7, a distance of 7 units away from 0. That's why we need to be on the lookout for multiple solutions when solving absolute value, because there's two distance numbers, a positive distance number and a negative distance number that are equidistant from 0 on the number line. But that could show up in a different part of the equation. So let's go ahead and take a look at my forward steps. Cover up to 25. Pretend you were evaluating in middle school by plugging in something for Q and doing your forward steps. The first thing would be times by 2. The second thing would be take the absolute value. So take the absolute value would be my second thing. And our last forward step, finally, we would add 7. So to get our solving steps, we're going to reverse and undo those forward steps. If the last thing we did was add 7, the first solving step will be to undo that by subtracting 7. So we'll subtract 7. Now comes the new thing. How do we undo taking absolute value? How do we undo taking absolute value? Adam?
Break it up.
Break it up. Break it up. And so we'll go ahead and break up the bars. That's when we split it into two paths, the positive distance number and the negative distance number. Thank you. And then lastly, we want to undo that timesing by 2. Easy cheesy. We'll divide by 2. Let's go ahead and apply those solving steps in order. First solving step, subtract 7 both sides. So we've got to subtract 7 both sides. That will get our absolute value expression, absolute value 2q alone on one side. Now we can go ahead and do our middle step, our favorite one, break it up, break it up. And so this is where we rewrite the expression without the bars. We're going to break it up into two separate equations. One, where my quantity inside the bars, in this case 2q, is set equal to the positive distance number. One equation where my quantity inside the absolute value bars, 2q, is set equal to the negative distance number. Remember, this is simply asking what two numbers are a distance of 18 units away from 0. Easy cheesy. 18 is 18 steps away from 0, but so is what?
-18.
Margo, you're fun. -18 is also 18 steps away from 0. So my break it up that I shared earlier, my break it up is when I set the quantity inside the bars equal to the positive distance number, and I set it equal to the negative distance number. Two separate equations. We've broken it up. Now you just finish it up into two separate equations. My last solving step was divide both sides by 2. So we're just doing it now to both equations in our path. So we got your, and I'm getting q equals 9 and q equals -9. Let's do a quick check of that -9. So my -9 into the original, 2 times -9, I can even use my green forward steps. -9 times 2 is -18. Absolute value of -18 is positive 18. Positive 18 plus 7, perfect. That does work. That's 25. So this is a solution, and we could do the same thing with our positive 9 as well. Okay. What questions are you having about our multiple solutions? So you will see questions that look like this on your quiz. What day is that quiz? Our first one that counts, not today's practice quiz. Day 7. Real quiz, counts into the campus. Today, practice quiz. The last 10 minutes, we'll take our practice quiz. Day 7. On your schedule, you can see it looks like for us, A-Day is Friday the 18th. So Friday the 18th is next week. Okay, let's go ahead and take a look at today's objectives. So today, we're going to move beyond evaluating expressions and solving equations to functions and relations. Today we're going to be able to identify relations and functions. We're going to evaluate functions, which is like evaluating expressions from your bell work. We're going to rewrite functions in different notations, and then we're going to correctly interpret and use terms such as domain and range that go along with our function and relation vocabulary. So we will need some vocabulary terms that are specific to our area of mathematics. Functions are mathematical models of relationships between two variables. Anytime we have a pairing of items, right, when the second item depends on what my first item is, we can talk about how that relation is a function. We're going to get more specific as we go on. So let's go ahead and get down some definitions on our note sheet so that we can begin talking about relations and functions and see the difference. So for our definition, a relation is any set of ordered pairs. Anytime we have a pairing of objects or items or numbers, we have a relation. A function is a special type of relation, a special type of pairing, in which each input, the first component, is paired with exactly one output, the second component. The dependent variable is the y value, the second component, or the vertical axis if I was going to make a graph. The independent variable is the x value, or the first component, or the horizontal axis on a graph. Two to go, and then we can start talking about what these mean. Input is the value of the independent variable in a function. It's my first item in the pairing. An output is a value that the dependent variable takes on, the second item in each pairing. If you guys would pause where you're writing and go ahead and take a look at this pairing I've written here on the front whiteboard. This is a collection of ordered pairs. It's a relation. A relation is just a set of pairings where the first element is paired with the second element. This is a pretty boring relation because it's just a list of points, ordered pairs, x comma y. But nevertheless, it is a relation. In this relation, my first component in each ordered pair is called the input. And so here, my third point, the input is -6. It's paired with the output 2. The fourth point, the input is -2. It's paired with the output 7. Right? So a relation in its most basic sense is simply a collection of pairings, right? Ordered pairs, like points, x comma y. A function is a special kind of relation in which each input, that is the first element in each pairing, is paired with exactly one output. And so anytime you see an input like 18, that 18 must be paired with the same thing each time in order to be a function. So if a member of this relation were 18 comma 7, and I look down the list and I had another 18, right, it better be paired with the same y value. Did I say negative 7? Negative 7. In this case, this relation is not a function. It's not a function. How come? Because the input, negative 2, appears more than one time. And in the second case, negative 2 is paired with an output 7 that's different than its original output. So this is not a function because negative 2 is paired with more than one output. Not a function. However, if we were to go like this, now suddenly this is a function because no input appears more than once. And so each input that appears is paired with exactly one output. This is a function now after I've erased that input. Margot.
So because it says, like the definition of input, it says that I have an independent variable in a function, but it's also in a relation to. It doesn't have to be a function to be an input.
I use input to represent the first element in my pairing, whether it's a relation or a function. Okay. Your book tends to use input when it's talking about functions specifically. I use it to denote the first member in each pairing is the input. The second member in each pairing is the output, or the y value, the dependent variable value. So I'll use them interchangeably. Great question. All right, now we're the last two. Domain. The domain of a given relation is the collection of all the independent variable values, the x values, the inputs, the first number. And so the domain of this particular relation includes the x values negative 6, negative 2, 2, and 4. It's just the x's, the inputs in a list. The range of the function is the collection of all the outputs, the y values, the second elements in each pairing. So in this case, the range would be the list of numbers 2, 3, 5, and 7. It's typically good math manners to list those in increasing order. We're going to go ahead and take a look at some of these together. So, a nice little graphic organizer for you guys. The domain is a set of possible values of the independent variable, or the first row in a two-row table, or the left column in a T-chart, or the inputs, right? All the inputs, the collection of those is referred to as the domain. The range is the set of possible output values, the dependent variable values, the second number in each ordered pairing, the second row of a two-row table, or the right column of a T-chart, and then the output, right, is the second element in each pairing. Let's go ahead and practice doing some evaluation with different notation. And so, a function f can be rewritten as a set of ordered pairs, as we've done on the board. It could be described in function notation, that's called Euler notation, by an equation y equals f of x. Or it could be defined by mapping notation. Mapping notation gives the name of a function and then takes the input variable and maps it onto the output variable. We're going to practice going back and forth between the different notations. In the past, you've seen this formula notation a lot. More and more, you'll see this function notation, this middle one. Let's go ahead and practice. If y equals 4x squared plus 7, then f of x, function notation, just replaces y with f of x. And so I could rewrite y as f of x. And then my same formula rule, 4x squared plus 7, is what I use for my rule. So if y equals 4x squared plus 7, so does f of x. F of x is how I read that function notation, often called Euler notation, after Leonard Euler, a famous mathematician. Now we'll write in mapping notation. In mapping notation, I still name the function. I name it f. In this particular case, my function f takes inputs and maps them onto outputs in accordance with the rule 4 times input squared plus 7. In each of these 3 cases, we still see our same function rule. Our function rule takes inputs, squares those input values, multiplies by 4, and then adds 7 last. These are just multiple representations of the same exact function rule. It's like different packaging, right, on your cereal box, right? It'll be the same contents inside, but they'll go through and they'll change the packaging on the outside, depending upon what mini movie's coming out next. Kind of a letdown after Despicable Me 2, wasn't it? You know what I mean? You know how I got there. I don't know. It's okay. All right. Let's go ahead and take a look at my super duper function machine. Took like an hour and a half to make this, but let's suppose for a minute now we're going on a magical mystery tour of the mind with Mr. Fritz. And if we were to reach into, right, this bucket is a collection of inputs or x values. If I was to reach into this bucket, the name of all the x values or the inputs would be the domain. If I reached into the domain and I grabbed a particular x value, a particular input value, and I put it into my function machine, according to some rule, it would perform some operations and pair it with an output value, a y value. A y value, right, that's an output, a dependent variable value. And if I caught all those outputs, all those y values in a bucket, what would the name of that bucket be? It would be the range. And so we've got our graphic organizer here. You can visually see that we reach in and grab x values from my domain. We input them into my function machine, and according to some rule like 4x squared plus 7, it'll assign that input value to an output value, a y value, a dependent variable value. If we caught all those y's together in a bucket, the name of the bucket would be the range. Okay, so this is a pairing. It takes input x's and pairs them with output y's. Let's go ahead and do some evaluation. So if there's a function t that accepts input values of c and pairs them with outputs in accordance with the rule 1.8 times c plus 32, I bet that this has something to do with temperature. So I bet that t has to do with temperature. I'm seeing this 32 jump out at me. Raise your hand if you think you know what that c might stand for. What do you think that c might stand for? Ben?
Celsius.
Celsius, this might be degrees Celsius. C, if I plug into this formula, it's going to output the temperature in degrees Fahrenheit, because we've got that 32 maybe. All right, that's what I'm thinking too. Let's go ahead and evaluate T of 20. So this is as easy as going to my function rule, and everywhere my function has a C, I'll replace it with 20. And so T of 20 is going to equal 1.8 times C plus 32. Except everywhere I see a C, we're not going to put C, we're going to put 20. Oops. So it looks like 20 times 1.8 is going to be 36. 36 plus 32 last is 60. Oh. There we go. 36 plus 32 looks like 68. Did I do that correctly? So if Ben is correct in his thinking that C represented degrees Celsius, let's go ahead and interpret our answer in the context of the problem. Go ahead and tell your partner quietly what this 68 means, and what T of 20 represents in the context of the problem. What do we just figure out then? And I'm going to call in a partner pair. Okay, enough talk. Now we eat. So what do you think, Kung Fu Panda? Always eating. No. So let's go ahead and share your interpretation complete with units. And so what do we think this T of 20 equals 60 represents in the context of the problem? Katie and Braden?
20 degrees Celsius equals 60 degrees Fahrenheit.
So 28 degrees Celsius equals 68 degrees Fahrenheit. Go ahead and raise your hand if you have the same interpretation. So do you have the same interpretation? Sorry, 20, yes, the whole time. The whole time I meant 20, thank you. Absolutely right. So that's also what I would guess. And does that make sense in terms of number-wise, right? From what you've heard, you know that lower degrees Celsius, right, lower degrees Celsius, when we're talking about daytime temperatures, correspond to higher number of degrees Fahrenheit. And that changes as you go backwards, right, as you go down into the freezing. It's kind of interesting when you interplay here. We're going to have to rearrange that. You'll see that again in your assignment and maybe later in class sometime. Awesome. Let's do another. We can also evaluate using mapping notation. So if we have a function named f that accepts input values x and maps them onto outputs according to the rule square root of 5 squared minus input squared, we can evaluate f of 3, and we can evaluate f of a variable expression, 2w. In each case, we simply take my input, rewrite my function rule, and everywhere my function rule accepts inputs, replace the input with my 3 or 2w in turn. So let's go ahead and rewrite that. F of negative 3 is going to take my function rule, 5 squared minus input squared. Everywhere I see that input x, I'm not going to put x, I'm going to put 3. Make sure we're following the order of operations, you guys. I have to do my squaring before I can do the subtraction. So I'll keep 25 squared is 25. I'll keep the subtraction, and I'll do the 3 squared is 9. Remember, I have to do that squaring before I can do the subtraction, which means I get square root of 25 minus 9 is 16. In some cases, this will reduce to an integer. In some cases, it won't. It looks like we do reduce nicely there. So 25 minus 9 is 16. The square root of 16 is 4. And we'll box the result so it's easy to see. We can even perform a function evaluation with a variable input. In this case, 2w is going to go in everywhere my function f accepts inputs. And so f is the name of my function. It accepts inputs, right, x, and maps them onto the output square root of 5 squared minus input squared. In this case, my input is 2w. So I'll still rewrite my function rule, the square root of 5 squared minus input squared, except everywhere I see an input, we're not going to put x, we're going to put 2w. There we go. Let's try it. Remember, squaring comes before subtraction, so I still have square root 25 minus 2w times 2w, 2w times 2w. I can actually do this without our exponent properties yet. We do 2 times 2 is 4, w times w is w squared, so this ends up being 25 minus 4w squared. So if I take 2w and I square it, that means multiply it by itself. And I get 2 times w times 2 times w. 2 times 2 is 4, w times w is w squared. Now, we don't know what w equals or doesn't equal, and so we're not able to go any farther. We don't do 25 minus 4w squared is 21w squared. We can't do that. These are not like terms. So stop. End of the road. What questions are you having about our mapping notation? Mapping notation? Okay. Then let's go ahead and practice going back and forth between our different notations. So we've got an example with an f function, a g function, and a function named a. We need to be able to rewrite in the different notation, either formula, Euler notation, or function notation, and mapping notation. In each case, you're given one box, and you need to fill in the 2 blanks. So what I'd like for you to do right now is with your partner, it's okay to talk. I want you to quietly work on figuring out what these blanks are, and I'm going to have you share your response, right, with the whole class on the smartboard. So let's figure out what would go in these blanks based on the given expression. 1 filled in, 2 missing. We'll do the first one together. If y equals 3x squared minus 5, then f of x also equals 3x squared minus 5. And the function named f takes input x's and maps them onto outputs in accordance with the rule input squared times 3 and then minus 5. There. 1 row done. Go ahead with your partner, figure out what would have to be in the other rows to complete the chart. Then be ready to share. Okay, ladies and gentlemen, thank you for those of you who came up and shared your response. I appreciate that. Let's go ahead and take a look at our second row. So if we have a function g of x, which is given by the square root of 2x plus 7, then we could write a formula y equals square root of 2x plus 7. We could also say g equals square root of 2x plus 7. Or we could say our mapping notation. Our function named g accepts input x and maps them onto outputs in accordance with the rule of square root of 2x plus 7. So here you could put y equals, right? Here you could put y equals, or you could put a equals, right? So either one is fine. In my name of my function, though, we want to make sure that we're being consistent. So this should be g and g, a and a, f and f. Good job. So it's okay right here if you have y equals. It's okay if you have y equals right here. They did give us the name a for this last one, so I'll probably do a for my formula. And my input k has to occur because it says my input is k. Right? So then this in parentheses, my input variable value, my independent variable inside my parentheses has to be a k. Awesome. Let's go ahead and take a look at your chart and make any corrections as necessary. Now let's evaluate. Let's find the value of g when my input is 8. It maps it onto outputs according with the rule square root of 2 times input, close radical, and then plus 7. Let's do it. So g accepts input values x and maps them onto square root of 2 times x, close radical, plus 7 last. So it looks like we'll plug in there. We'll do the 2 times 8 first. Then we'll do the square root second. Square root of 16 reduces to 4. Still have that plus 7, just chilling. And lastly, we'll get 11. Yes, Adam.
Couldn't you have the negatives, the positive and the negative of those square root of 16?
Great question. So we've seen, right, in our activity and in our notes today, when we're solving a squaring equation, there's two potential solutions oftentimes, because when undoing a squaring, we must consider both the positive and negative square root. That is, there's two quantities such that when squared, equal a given result. The difference with this, g of 8, is that we're evaluating a function rule that's already in place. We're not creating the radical to undo squaring. We were already given a radical, and this radical didn't have a plus or minus in front of it. It just had nothing in front of it. That's assumed to be the positive square root. And so only when we create the radical as an inverse operation to undo squaring do we need to consider the two possible solutions, one given by a positive square root, one given by a negative square root, and that could be an intermediate step. The difference was we were evaluating the function rule. It was given as a single radical. We'll just do a single radical and a single value. Great question. But we were given a radical here. We weren't creating one. If we're creating one as a means to solve equations, then we need to again look out for two. You see the difference? Great question. F of negative 3. Do it. Go ahead and plug in negative 3 to your function. Do it. Show your work. Be ready to share. Watch your order of operations. We know when we take a negative number and square it, right? When we square it, we do the exponents first. Negative 3 times negative 3 is positive 9. I have not multiplied by the 3 yet out front. We don't do 3 times negative 3 first, right? And get negative 27 and then square that. No. We do the squaring before we do the multiplication. Then we do the multiplication before we do the subtraction. And finally, we can get our final answer. Raise your hand if you already had 22. So you already have 22? Awesome, great, thanks, hands down. And one more with fractions. If I take 3/4 as an input and plug it into my function rule for A, everywhere A accepts inputs, in this case k values, it looks like I've got some fractions within a fraction. Let's see what that looks like. So everyone, let's rewrite our function rule, A of k, which is given by k squared over 8, except everywhere we see a k, we're not going to put k, we're going to put 3/4. Recall that 3/4 squared means 3/4 times itself. 3/4 times 3/4. So as I'm working out my intermediate steps, I do squared before I ever do division by 8. I'll do 3/4 on top times 3/4. Still all over, go gadget arm 8. Recall your rule for multiplying fractions is straight across. So this equals 3 times 3, 27, over 4 times 4, 16, and that's still all over 8. So all we've done so far is squared 3/4. I'm sorry, 9. Bad with numbers. Great with variables, letters, bad with numbers. Thank you. 3 times 3, turns out that it's 9. Second time this class. 3 times 3 is never 27. I'm thinking 3 cubed.
It's okay, it's early.
First hour. 3 times 3 is 9, over 4 times 4 is 16. Is that right? Thank you, guys. Now let's go ahead and finish it out. How is it that we divide when we're handling fractions? No problem. I know that division with complex fractions, dividing is the same as multiplying by the reciprocal. So if I take 9/16 and divide it by 8, that's the same as taking 9/16 and multiplying it by 1/8. So we'll go ahead and rewrite the next step. We'll leave my 9/16 alone. Instead of dividing by 8, that's the same as multiplying by 1/8. Yep, multiplying by 1/8. And now I can do straight across. I'm confident this time 9 times 1 is 9. 16 times 8 is 8 times 10 is 80. Plus 8 times 6 is 48. So I'm getting 128. I think 128. And seeing that 128 is made up of just 4s and 4s and 2s, it's not going to reduce it to 9, so I know that's my final answer. Take a minute to make sure you have your function evaluations correct. And now I'll go ahead and change my question around. So you guys have done a good job evaluating a given function rule for a particular input value. This is a different question. For what values of x does f of x equal 13? In this case, are we plugging 13 into my equation everywhere I see an x?
No,
No, right? What's different about this, Margot?
the equation equals 13.
The equation equals 13. Good. So my f of x is going to be replaced with 13. And so we'll go ahead and rewrite, right? We'll rewrite my equation, except my function value, f of x, is going to be replaced with 13. And we're going to solve for x to see what input values, what x values are responsible for producing the output 13. We may or may not be able to do this. However, I've got a good feeling, right? A good feeling that we're comfortable solving squaring equations. We've seen this in the past, and we're going to go ahead and use my strategy, my reverse and undo. So if I were to cover up my equation, and I were to pretend I was in middle school evaluating this expression, and plug in something for x, the first thing I do is square it, then times by 3, and lastly, subtract 5. So we'll go ahead and reverse and undo to get my solving steps. If the last forward step was subtract 5, my first solving is going to be add 5, divide by 3, and now that I'm undoing a squaring, to solve, that's when we have to consider both the positive and negative square root. That's when I have two potential answers. Let's do it. First step, add 5 to both sides. Second solving step, divide by 3, both sides. Last solving step, take the positive and negative square root. That is, if x squared equals blah, then x is given by the positive and negative square root of blah. In this case, x squared equals 6. And so x will be given by the positive and negative square root of 6. Sometimes this will reduce, sometimes it won't reduce. But in either case, I have two separate answers. We saw this on your activity. Your activity, the last one, wasn't a perfect square inside the square root. Unlike our earlier examples, when we ran into nice perfect square numbers inside a radical, like 16, the square root of 16 reduces to an integer 4. Does the square root of 6 reduce to an integer? No, and so I'll leave it exact as the square root of 6. If I wanted to see what that was on a number line, then I could go to my calculator and do square root of 6 and see about what that is. For now, I don't want to lose accuracy. I'll leave this as exactly x equals square root of 6, or x equals the negative square root of 6. Notice how we have two different answers. We've left them exact. Once we change it to a decimal, we're sacrificing accuracy. We're losing accuracy. So I'll go ahead and leave that as a radical. Awesome. So it looks like when x equals square root of 6, f of x equals 13. When x equals negative square root of 6, f of x equals 13. What ordered pairs would be represented by these solution values and function values? How could I write that as an ordered pair? Could I write that as an ordered pair? Adam?
Square root of 6 or square root of 6, and column 13.
1 point. A second point. Both of those points would be in the relation x comma f of x. It turns out this is also a function. Every time I put in root 6, I'm going to produce 13. So both of these ordered pairs are in the function x comma f of x. Awesome. Good job. So if you didn't see it again the first time, I reach into my domain, just since I spent an hour and a half with the color coding. I grab my input variable x. My function rule assigns it to an output value, a y value, right? By working out some function rule to my input, it pairs it with an output. If I caught all those outputs, those dependent variable values in a bucket, the name of that bucket would be the range. Okay, So for our closer today, I'd like for you to go ahead and fill in the blank. Don't say it out loud though. Okay, don't say it out loud. Just fill in the blank. I'm going to have you guys share. The collection of all inputs is the blank. Don't say it out loud. The collection of all outputs is the blank. In the function g of m, which variable is the independent variable? Which variable is the output? Which variable is the argument? And lastly, if p of n equals the square root of quantity 4n minus 5, then p would take 9 and map it onto question mark. Go ahead and show your work, please. Okay, we're going to talk about these together. Thank you for writing your responses down. I see that several people have left the last one, number 3, argument blank. That's okay, we're going to talk about it together. Okay, for now, let's go ahead and share your response. When I call and you share with the entire class, the collection of all inputs is called the blank. So the collection of all inputs, what do we call the collection of all inputs? Dakota? The domain, good. The domain is the collection of all x values, of our input values. The domain is the collection of all the first elements, right, in a pairing. Good job. Thank you. The collection of all outputs, right? The collection of all outputs, what's that called? Logan?
Range.
The range. So the range is the collection of all my y values, all my outputs, right? All my dependent variable values. If I caught those together and put them in a bucket, the name of that bucket would be the range. Thank you. Good job on the first two. So let's go ahead and check. In the function g of m, which variable is the independent variable? So which variable is the independent variable? Aaron? M. Thank you. So I remember that. I think of this as independent variable is inside the parentheses. My input. The input is inside the parentheses in function notation. So m is the independent variable. Because this question asks which variable is the output, I would say g, right, is the output. So I would say g is the output. G of m, I'd say, is the function, right? G of m is the function, I'd say, and so I just put g for the output, and that's kind of a technicality. My argument is in the reading. We didn't talk about that today in our discussion. The argument is just in the textbooks a different way of saying input variable. And so argument is the same as independent variable. It's inside the m. We're not talking about getting in a fight over this, right? We're not getting in an argument over this. It's just that my input variable m is also called the argument in some textbooks. So I want you to be aware of that. And lastly, the function evaluation. Casey?
I was just curious why the independent variable was n. I just didn't really get that.
No problem. So in my independent variable, let's do this. So in each of these cases, what are we plugging into my function rule in order to pair with an output? We're plugging in this function rule, we had x's in my formula. In this function rule, we had x's in my formula. In this function rule, we had k's in my rule, right? Here in my function notation, my input value is right inside the parentheses. It's basically telling me what input variable I'd expect to see if I look at my formula, if I look at my function rule, right? In this case, I see k's in my function rule. In this case, I see x's. Do I? Yes. In my function rule, there's x's in my equation, in my formula. So the input variable is inside the parentheses in each of those cases. What was inside parentheses here? M. If I had this written out as a rule, I'd expect to see blah, 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 m squared minus 2m plus 6. You know what I'm saying? I'd see m's in my rule. Great question. All right, are we ready to do it? Yes, we are. What's my independent variable? My input variable in number 4. Then, Casey?
Oh.
What would be my input variable in number 4?
9.
Yes, 9 would be my input value, but what variable would be my input variable? N, absolutely, it's inside the parentheses. It's what I'd expect to see in my function rule. Thank you, that's perfect, let's do it. So I'm going to replace N with 9. So I've got 4 times parentheses 9, close parentheses minus 5. Everywhere I see N, I replace it with 9. Watch your signs. 36 minus 5. We'll perform the subtraction first. 36 minus 5 is 31. Then the radical last. Sometimes this will reduce, sometimes this won't. Do I need positive and negative square root of 31? Were you creating a radical to undo a squaring? No, you were given a radical, so we're already just evaluating a single radical. If there were a plus and minus here, then we do 2. But in either case, we weren't creating the square root as a means of solving a squaring equation. We weren't creating square roots to undo squaring. We're not solving the equation. We're just evaluating in accordance with the function rule. Who already had square root of 31? Did anybody already get square root of 31 at the end? That's awesome, you guys. Way to go. Great work today. So we'll go ahead and box this. I'm going to export these notes as a PDF file, and you'll be able to find that in Moodle. Recall, you can go to the high school webpage. At the high school homepage, you can click on that hot Moodle button in the middle, and then advanced algebra, math. And then advanced algebra is the very first math Moodle. You can click on that and log in as a guest. You don't need a username as a password. I'm also going to save our audio file and hyperlink that as recorded, right? As the recording. You can find those in our Unit 1 if you scroll down in the calendar. Nice job today, you guys. What we're going to do is take a look at the moment you've all been waiting for. No, not that moment, Jackson. We're going to take a quiz over solving equations and rewriting formulas, but don't worry, it's a practice quiz. You should have already picked it up from the roller cart. But what we're going to do is we're going to take this opportunity to practice your solving. We will check it next class. And so let's go ahead and close your notes, put everything away, and we're going to work quietly on your practice quiz 1617. You're going to show your work, and we're going to treat this, right, as if you were doing a real quiz. And so no notes, right? No notes, no partner. You don't have to move the desks, but you're not going to work on this with your partner. You're going to try to do it on your own by yourself. Okay? Then we're going to go ahead and check it. Don't lose the quiz. We're going to check it and grade it next class, Thursday, so you can see exactly how the worked out solutions look and use this to study from. So once again, practice quiz now, by yourself. No calculator and no partner. You don't need to use a calculator, because you can just show your work in the art of operations. Good job. Excellent. Thank you.